Hi everyone, I am Satyam. I'm a software engineer at Mirantis. I'm with the open source program office where we contribute to cutting edge technologies from cloud to AI. I'm excited to have you all here for this session. And if you are working in platform engineering, DevOps, building AI infrastructure, or launching GPU backed services in sovereign regulated markets, this session is for you. Let me give you a little bit of context. So, we are in this future where AI is no longer just software, it's hardware hungry sport. The study by McKinsey, if you look at the charts at the right, the study projects that AI grade data center capacity must climb 33% year till 2030 to meet the rising demand. At the same time, hyperscalers are on track to control nearly two-thirds of global compute capacity by 2030. And so the cost of GPU backed instances has skyrocketed as demand surged. There is another analysis by Uptime Institute's 2025 where they note that renting on demand DJX H100 NVIDIA instances averaged $98 per hour at hyperscalers, while emerging neoclouds offer similar capability for about $34 per hour. And that's a 66% savings, and yet still leaves sovereignty gaps. So if the demand is exploding and cost is painful, what exactly must an AI cloud platform deliver? So this surge in demand exposes four blockers. First, we have time to value. Many organizations still wait weeks or months for a GPU cluster, and the fact that GPU clusters still spin up like legacy VMs, onboarding drags on for weeks, leaving customer waiting. Second, we have developers and data scientists don't want to operate infrastructure. They need an instant, seamless access to resource so they can experiment, iterate, and deploy without friction. Third, we have multi-tenancy. So multi-tenancy has gone from nice to have to table stakes. Modern GPU hardware now provides hardware-level isolation for safe tenancy, a must when multiple research groups share scarce accelerators. So therefore, secure multi-tenant scheduling is the key to keeping costly GPUs busy. And lastly, we have data sovereignty and future proofing. This is from drives like EU tech sovereignty drives and other initiatives which are forcing providers to keep data local and avoid hyperscaler lock-in. And so sovereign cloud providers or regional telcos must meet strict data locality and governance requirements while delivering these modern AI services. So traditional VM-centric infrastructure as service can't meet those agility, utilization, and compliance needs. So we need a different foundation. So we have Kubernetes, which is an industry standard orchestrator for containerized environments and has become a common base layer. And that's because Kubernetes spans bare metal VMs, public clouds, new clouds, and even edge sites. So out of the box with Kubernetes, we get self-healing, horizontal scaling, and a thriving open source ecosystem. And that's exactly the bedrock that AI platforms need. And when we combine these Kubernetes capabilities with open declarative tooling, you can build GPU clouds that stay vendor neutral and scale elastically and plug into sovereign data centers. So Kubernetes is our runaway, but anyone running more than a handful of clusters knows that the new problem appears, and that's Kubernetes sprawl. So Kubernetes everywhere means clusters everywhere. There is a study by SpectroCloud which reports that 56% of companies already operate more than 10 clusters and 69% run them in multiple clouds. So what that means is with more clusters, we have more patches, more policy drift and configs, and thus precisely drags the AI initiatives back into toil. So how do we tame this Kubernetes sprawl while keeping all the benefits that Kubernetes provides? Here is how we can tame that sprawl. I'm going to introduce Cordant AI. It gives a single pane of glass for any footprint. OpenStack, bare metal, AWS, Azure. So everything rolls up into one control plane. With it, we get declarative GPU service templates. Those are like reusable blueprints that bundle the NVIDIA or AMD GPU operator related drivers, monitoring, and RBAC. So with it, you get one click, or you want to do kubectl apply, and a compliant GPU stack lands in every chosen cluster. With Cordant AI, we also have hard multi-tenancy boundaries, which keep workloads isolated and data where it's illegally allowed to live. So while Coordin's built-in FinOps and observability layer feeds OpenCost metrics straight into Grafana, so platform teams can see the GPU utilization, the cost incurred in real time, and one can also right size before bills explode. And also, it's integrated with AI inference services, so schedule, service, and lifecycle models with smart routing that keeps data in the right jurisdiction. We also see in the end of these slides how a sovereign cloud provider uses Cordant AI to run regulated AI workloads. So now let's take a step back and we'll look at the base infra setup for Cordant AI, which is made possible by Cordant. So Cordant AI is based on open source Cordant and based on open standards. So you can swap in components or proprietary AI pipelines as well. So under the hood, Cordon's cluster management layer provides the provisioning and scales infrastructure, while there is state management, which keeps add-ons frictionless. And it also has built-in FinOps and observability that can track GPU utilization and cost end-to-end. This is the Cordon's architecture. Cordon builds on familiar upstream projects. If you've heard about CAPI, it's a project under Kubernetes special interest group. So think of the first component KCM, which is based on CAPI, as your day zero automation. It's using cluster API to spin up clusters declaratively and manage the lifecycle of clusters across public clouds, OpenStack, and bare metals or on-prem in exactly the same way. Then we have KSM. So KSM handles day one plus operations. It deploys workloads or add-ons, let's say GPU operators, ingress, secrets engines into any or all clusters via declarative service templates. So platform team push one manifest and KSM fans it out consistently across clusters. And we'll see while I'm demoing the service templates which live in the catalog.cordant.io, which is completely open source. And then finally, we have COF. COF is observability layer for Cordant. It's built with OpenTelemetry collectors, Prometheus, Grafana. And so COF snaps in like Lego bricks. So logs, metrics, and traces out of the box. And plus, we also have cost data from OpenCost, which is deployed on the clusters. So platform owners can see health, performance, or spend for every cluster. So what does that all look like in practice? We can turn this one YAML into a running GPU cluster. So if you look at this YAML, there are two important things that I want to highlight. First is the template that we have used, the first thing on the spec. Using this template, we get a reusable blueprint to define our cluster configuration. We are saying to KCM component that we need a cluster with one control plane, two worker nodes in South India. And we have also defined the VM. For the control plane, it's standard A4v2, while for the worker, it's an NVIDIA standard NC4. And because we have an NVIDIA GPU-based nodes, so we want to be able to discover that. So that's where we define a service. And the service uses, this is the other thing, the service uses a template GPU operator using with which we can define that we want a NVIDIA GPU operator in this cluster. And because these templates are version pins, we get reproducible builds with guaranteed compliance boundaries. So this is the result. With one YAML, we have fully compliant GPU-enabled Kubernetes cluster. With that, we have a demo. So for this demo, we have a Cordant COF setup. This is our management cluster, which is living on Azure. And in the management cluster, we have KCM system namespace where we have the core components of KCM deployed, which are CAPI controllers and the controllers provided by the different infra provider, including Azure, AWS. So this is Kappa, CapZ for Azure. This is all running. We also have a different namespace COF where we have operators related to OpenTelemetry, Prometheus, Grafana running, and it provides the very comprehensive observability layer for Cordant. So this is our mothership cluster or management cluster. We have another cluster which I call it a regional cluster on AWS. Okay, so with these two, I'm gonna quickly spin up another cluster And this is our another child cluster on Azure, and where we just saw a template in the last slide where we define another cluster deployment to deploy a cluster with a GPU-enabled node. So there we have a configuration for one control plane, one worker node in the South India location, and we define the service GPU operator to be able to discover it and further services to enable observability. Okay, so because this cluster deployment is using this service GPU operator, we need a service template for that in our mothership cluster. And that's where catalogs comes into the picture. We can go to catalog.cordent.io and we're gonna get an NVIDIA GPU operator. We can just copy it from here for installing on our management cluster. I'm gonna export my kubeconfig so that I can access the Azure management cluster. Let's check if it is good or not. So this is our management cluster on Azure with 3 nodes. That's all right. I'm going to install the NVIDIA GPU operator service template here. It shouldn't take much time for me because I already pulled it. All right, we have service template. Let's check that out. kubectl and KSM system. And we see that we have a GPU operator service template, which is valid now. And now we can deploy our cluster deployment. And if you notice, we also have the credential. So I have a credential to be able to provision infrastructure on Azure. Now I'm going to apply this cluster deployment. The name is Azure Child. And we see that it's being created. We can also verify that in our management cluster, checking out the logs of capz. So this is our capz. And if you see the logs, okay, so we have Azure machine, which is being reconciled. What I can do is I can get the status of the cluster deployment by getting cluster deployment object. And this is called Azure Child 0. Okay, so it's still in false because we have 0 by 1 services, so the NVIDIA GPU operator, and then we have infrastructure message, which is it's getting ready. And because we are using CAPI under the hood, we can also do cluster CTL, describe cluster, and we're gonna put the name of our cluster. And let's check. So we see that the only thing which is ready for this infrastructure is resource group. And we're gonna wait for some time for it to be able to come up. Meanwhile, what we can do is because we have OpenTelemetry related operators deployed, we have an observability dashboard for all the clusters across all the regions on any cloud. So I'm going to port forward to. So this is my Grafana service, which is running in the Kop namespace. I can just port forward to it, and I should be able to see it here in the localhost 3000. So we have this Grafana dashboard. And if we check out the dashboards, we have cluster monitoring and nodes. I can see a number of clusters that I can choose from. So right now, let's choose the mothership or the management cluster that we have. And we can see the resource utilization for it. And similarly, we can choose another cluster, let's say my regional one, and I should be able to see for the same. What else do we have with the KOF observability layer is a number of things. One of the other things is the cost incurred by a cluster, which is being exported by the OpenCost controller. So for our mothership cluster, which is running Azure, this is the cost incurred. For AWS, we have a different one, and we'll see for the ones that we just created out as Azure Child 0 once it is available to us. So let's quickly check out the status for the same. So now we have a number of things ready, but still a few things are remaining. And I can check the same using getting the status for the cluster deployment. So control plane is initialized and other things are initializing. So this is the catalog repo with a number of services that one will be able to deploy on their across their clusters, including Argo CD, networking layer, Knative. Okay, let's check out if our cluster deployment is available yet. No, it's not available. So while that's happening, I could introduce you to one of the niche concepts of Cordant, which is of course service templates. So if you see this dashboard, we have real-time observability from different clusters. We can see the resource utilization, cost incurred. On top of it, what Cordant also enables us to have our own beachhead services, so which could sit in the mothership cluster and operate as we want. That is possible through a multi-cluster service, and we're going to leverage that and turn this real-time observability into getting the future trends for the same clusters. That's using a small project called FinOps agent, which is going to sit in the management cluster, collect metrics from the various clusters we have. It aggregates at one place and uses open source zero-shot Datadog Toto model for forecasting. So while our Azure cluster comes up, let's see, still a few things are remaining. I'm gonna spin that little application. I'm gonna go into the project and let's check it out. What do we have? How do we deploy this application? So I have an application which is written in Python, and there are a number of things defined for it. What we are most interested in is in deploying it on the Cordant. So we have this service template where we just reference the Helm repository for the FinOps agent, and we create a beachhead multi-cluster service referencing that service template, and we have labels which make sure that service is in the management cluster, or we want to deploy it in a number of clusters, any of the clusters that you have. So this is the configuration for it. I'm going to apply this configuration. I'm going to start with the Helm repo for the same. Okay, we have Helm repository created. The next thing we're going to do is create the service template for the same. Now we can check the service template using kubectl get service templates and KCM system, and we have a number of them. The one that we're interested in right now is FinOps agent. So now that because we have the service template, we can deploy this service in any cluster, in any namespace that we want. That's using the multi-cluster service that we have defined here. I'm going to apply this last multi-cluster service. And now we have the FinOps agent running in our mothership. We can check the FinOps namespace for the applications to come up. So we see there is a pod running for it. We also have configuration. For the sake of time, I'm going to make sure that it runs fast enough. So I'm going to look back to 2 days of, let's say, OpenTelemetry data from our clusters for every 1 hour. And then we're going to forecast for 3 days ahead using the Datadog model. And because it's a GPU-enabled cluster, I'm going to use CUDA. And we can do the num samples to 256. And we should be good. Let's just let it come up. Okay, let's go back and check if our Azure cluster is up. All right, so we have a new cluster now running. So this is our management and the existing AWS cluster. And we have another child cluster, which we are going to see up in our Lens dashboard in a moment. So because we have this cluster, we're going to get the kube config for it. And I can do that using kubectl get secrets. We have it now stored in Azure child kube config. I can just add, it's already there. And I can see the pods running on this new cluster. Okay, so NVIDIA GPU operator is coming up. And we have also the COF for observability of this. They're all coming up. Let's check out the nodes. Kubeconfig. So the nodes are ready, and we have pods running, which are going to come up, and we'll see the new cluster in our observability dashboard as well very soon. Okay, so that's our turnkey GPU deployment. And if we go to the nodes, we'll see it in the drop down. Okay. All right, so we have something here. Let's look at the other thing, which is our FinOps agent, which I just deployed as a beachhead service on my management. So if we look at the pods, it's running. Let's take a look at so yeah, we have forecast for a few clusters. Let's check out if it's coming up on our dashboard. All right, if you see, we have a new dashboard here, forecasting dashboard, which was also deployed along with the service for FinOps. And let's take a look. So it's not yet there because the application is still running. We're going to see that in a moment. It should be there now. We have the model accuracy, number of clusters for an average MAPE for the accuracy of the model, 6.7%. We also have the cluster level forecast. Yeah. Now, if you see this, this is 0.22 for AWS Ramesses Regional. If you observe the dashboard for OpenCost, this is close to what we have. So the middle line is our mean values, the 0.50 quantile, or the mean value for the forecast for the next 3 days. Upper one is 90th percentile, lower is 10th percentile, but this is where we're most interested. Similarly, we have cluster CPU utilization and memory utilization. And I can do that for, let's say, mothership. And for that also, I have some data. Okay, and this is using a beachhead service on the mothership, on the management cluster. All right, let's get back to the slides. That's all for the demo. So what we really saw is one deployment for turnkey GPU cluster. And now that we have proven live GPU turnkey with Cordon, now let's see a customer at scale. So this is the real world use case of Cordon AI. So there's this Dutch provider Nebul, which is based in Europe, that runs regulated AI inference. They used Cordon AI to consolidate OpenStack, bare metal, and VMware instances into one control plane, and then launched on-demand GPU service across Europe. And with that, that's all for today. Thank you for tuning in.